So we are going to talk about the rational and Jordan canonical forms of matrices using fx modules. To start off, let's suppose we have some fx module M, which we can write as a direct sum of cyclic modules like this. We're also going to assume that these elements here, f of x, all have leading coefficient 1. Since f is a field, we can always divide by the leading coefficient since it's a unit, and we're still going to get the same ideal down here. So without loss of generality, we can say these have leading coefficient 1. Now we know since M is an fx module, it's a vector space. So let's first think about finding a basis for this form of M, and then we can start thinking about what does multiplication by x look like. Since M is a vector space over F, our goal is to find a basis for M over F. Now, a basis has to generate every element of M. So let's think about what we need in order to generate the elements of M. To do that, let's take a look at one specific component of this direct sum. Say it looks like fx mod f of x. In that case, the elements in this module are going to look like c0 plus c1x plus dot 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 plus c d minus 1 x to the d minus 1. And in this case, I'm writing d to be the degree of the polynomial f. And this is because once we get to anything that's degree d or higher, we can use the fact that f of x equals 0 in this quotient to reduce it down, to reduce down the powers until everything is d minus 1 or less. Let's consider this set 1, x, x squared, and so on up to x to the d minus 1 of elements in our module. We want to consider whether this is a basis over f for our module as a vector space. To do that, let's first consider the possible linear combinations of these elements, the linear combinations of powers of x. Well, in this case, we're looking for a basis over f, so the coefficients are going to be in the field f. The linear combinations are going to look like c0 times 1 plus c1 times x plus c2 times x squared and so on, all the way up to x to the d minus 1. And each of those ci's is going to be an element in f. But notice that this form here, this linear combination, is exactly the general form of a polynomial in our module. And therefore, for any polynomial in our module, we can write it in this form, c0 plus c1x plus c2x squared and so on, which means that these powers of x are able to generate every possible polynomial over f. So this is definitely a generating set. Additionally, if this is the general form of our linear combination, then if this linear combination is equal to 0, we know that's only possible if all of the coefficients are equal to 0. And therefore, this set of powers of x is also linearly independent over f. And since this is a generating set that's linearly independent, we get that these powers of x up to x to the d minus 1 are a basis for our module over f. Now, from here, this gives us a basis for one of the components of the direct sum. If we want to generate the entire direct sum, all we have to do is take this generating set for each of the components of the direct sum separately. And if we put those all together, then we can generate the entire module. And of course, if two of the elements are in different components of the direct sum, they're definitely linearly independent. So putting those all together, this gives us a basis for M. And we can write down any of the elements of M as a vector using these as the basis vectors. So let's think about how we would write that as a vector. Now let's remember why we use vectors in the first place. Once we have a basis for a vector space, we know that every element in the vector space can be written uniquely as a linear combination of the basis elements over f. Once we specify a particular basis, every single element in the vector space is determined by the coefficients for each basis element. If we already know the basis, Instead of writing the linear combination explicitly every time, we can just list the coefficients in a specific order. And then when we read off the vector later, we can tell that the first element corresponds to 1, the second element corresponds to x, the third goes to x squared, and so on. So it gives us a more compact way to express that linear combination of the basis elements. So let's start by listing the coefficients in the first polynomial. I'll write it like this: C10, C11, C12, and so on. So CAB is the coefficient of x to the b in the 8th polynomial. So once we list all of the coefficients for the first polynomial, we're going to go to the second polynomial. So we'll have C20, C21, and dot, dot, dot. And then once we finish the second polynomial, we do the third, and so on and so on. So each of these blocks in the vector is going to generate one of the components of this direct sum. And once we put those all together, this vector describes the coefficients of every single polynomial in this direct sum module. Because M is an fx module, multiplication by x is described by some matrix A. So now we need to figure out what that matrix looks like for this form of the module and this specific basis. Now when we have a matrix that describes a linear transformation, each column of the matrix tells us the vector that we get when we apply the matrix to one of the basis vectors. So all we need to do now is figure out where the matrix sends each basis vector. It's important to remember while we're doing this that the whole point of this matrix is to describe multiplication by x. A times the vector should be the same thing as x times that element in the module. So when we think about what happens when we multiply the matrix by one of the basis vectors, the way we want to figure that out is by going back to the original module, saying what does this basis vector look like in the module, and for that basis vector, what happens when we multiply by x. So let's think about what that looks like. All of the basis vectors are going to look like x to the k. And so what happens if we multiply by x? X times x to the k equals x to the k plus 1. So it's actually really easy because x to the k plus 1 is another one of the basis vectors. So if we take the matrix A and we multiply it by the vector, say this is one of the polynomials, it has a 1 here and a 0 here, and so on. So everything else is a 0, but this gives us one of the basis vectors. Applying the matrix to this is going to take the x coefficient to the x squared coefficient, x squared to x cubed, and so on. So it's going to take 0 to 1, 1 to 2, and on and on. So we're just going to go one step down in the vector. It's going to be dot, 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 except instead of 1, 0, it's now going to be 0, 1. So we've moved to the next coefficient. And this works for almost all of the basis vectors. The only case where it doesn't work is x to the d minus 1. Because what exactly happens in that case? Well, in that case, we're going to have the same thing, x times x to the k equals x to the k minus 1. But when we do that, we're going to get x to the d. This is not one of our basis vectors. But remember, we can reduce x to the d using the fact that f of x is equal to 0 in this quotient. So let's take a look at that. We know that f of x is going to be described by some polynomial, a0 plus a1x, and so on. And we said at the very end that it was leading coefficient 1. So we just have x to the d here with no coefficient. Now we're looking at the quotient, so the way that works is we take f of x and we say that is equal to 0 in the quotient. And so now we have a way to express x to the d. If we just take this entire thing and subtract it, move it to the other side, then we get x to the d equals negative a0 minus a1x minus dot 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 a d minus 1 x to the d minus 1. And so this gives us an expression for x to the d, but in particular, these are all in terms of the basis vectors that we have right here. So let's think about what this looks like when we describe it using the vectors. We're going to have a times, this time the vector is going to be ... 0, 1, but this 1 is the very last one. It's the last basis vector here. And when we do that, x times x to the d minus 1 is x to the d, and we just showed that's equal to this expression. So it's going to look like this. Here, inside of this part, we're going to have negative a0, negative a1, negative a2, and so on, negative a d minus 1. When we multiply the matrix onto x to the d minus 1, we end up reducing it like this, and so that's the vector we get as the result. So now we have the output of the matrix for every basis vector, and all we have to do to write the entire matrix is just to put the output at each basis vector in the columns of the matrix, starting with the very first one. So let's see what that's going to look like. At the very top, the first basis vector is going to be 1 in the very first polynomial. So we're going to have a 0, 1. So when we start with a constant and multiply by x, we go to the next component, which is the x basis vector. After that, if we start with x and then multiply by x, we're not going to get any x, but we're going to get x squared. And then if we multiply x squared by x, we're going to get x cubed. So we get the same thing, 0, 1. And then we go ... all the way to the very end. And for the very last vector, instead of a 0, 1, we're going to get negative a0, negative a1, negative a2, ... negative a d minus 1. So in this block, we have zeros along the diagonal, we have ones below the diagonal, and then in the very last column, instead of this 0, 1, 0, 1 pattern, we have all of the coefficients of f of x, except they're negative. Now this gives us what the matrix looks like for just one of these components of the direct sum. The entire matrix is going to be a block, because if we multiply one of the things in the second polynomial by x, it's not going to suddenly go to the first polynomial. It's going to stay in the second polynomial, which means that something that's in the second block is going to stay in the second block when we multiply by the matrix. Now the second block is the same thing, it's just another polynomial. So it's going to look exactly the same as this, except we're going to have different coefficients here. So it'll be 0, 1, 0, 1, blah, blah, blah. And then all the way over here, maybe b0, b1, and so on, b d prime minus 1, because it's a different degree. And then after that, we might have even more blocks. And we're going to go ... like this. And that gives us our entire matrix. So if we want to take some arbitrary element in this module and multiply it by x, we can put all its coefficients in a vector down to the bottom and then multiply it by this matrix. And I'm not writing every single entry of the matrix because then it gets a little bit cluttered. But the idea here is anywhere that I didn't write a number, the number that goes there is 0. So everything in this block is a 0, everything in this block is 0, and everything here where I didn't write a number, these are all zeros as well, above and below these diagonals. So this matrix here gives us a complete description of the module, because the number of rows tells us how many components there are in the vector space, and then this matrix tells us how we multiply by x. Now, in the specific case where we're looking at this module, and these f of x's, these functions, are the invariant factors of m, then we say that this matrix A is in rational canonical form. Now we showed this rational canonical form of the module when the module is a direct sum of cyclic modules like this. So you might think this isn't super widely applicable because this is really just a special case. But in fact, it applies very, very widely to a lot of modules. And let's see why. Suppose that M is a finite dimensional vector space over F. In that case, the dimension of M over F is finite, let's call it n, and then let's consider the set of vectors for any v in the vector space. We'll look at v, xv, x squared v, and so on up to x to the n v. Now the number of vectors here is n plus 1, but because M is an n-dimensional vector space, n plus 1 vectors have to be linearly dependent. In other words, there is a linear combination of these vectors that adds to 0. But if we have a linear combination of these vectors and we factor out the v, that's going to look like a polynomial times v. And this polynomial is an element of fx, which means that if we look at this v as an element in the fx module, there's a non-zero element that sends it to 0, since these vectors are linearly dependent, and that means that every single element in M is torsion. In other words, M is a torsion fx module. And we also know, because M is finitely generated over the field, it's also going to be finitely generated over fx, because we can just use the exact same generators. And therefore, any finite dimensional vector space M is a finitely generated torsion fx module. And we showed in a previous video, link in the description, that every finitely generated torsion module over a PID is isomorphic to a direct sum of cyclic modules. Fx is a PID, it's actually a Euclidean domain, and therefore every finite dimensional vector space with a matrix is isomorphic to a direct sum of cyclic modules. So we know that any matrix that has a finite number of rows and columns is going to be associated with a finite dimensional vector space. So for every single matrix, if we look at the fx module where that matrix describes multiplication by x, we can write that module as a direct sum of cyclic modules. So let's suppose we have some arbitrary matrix B, which is an n by n matrix over F. Then B is associated with an n-dimensional vector space, so we can describe an fx module, which is finitely generated and torsion, where B describes multiplication by x. And therefore, that module is isomorphic to a direct sum of cyclic modules. So the module fnb is going to be isomorphic to something that looks like this m here, where the multiplication by x is described by a rational canonical form matrix. The thing here is we proved in another video, link in the description, that if two fx modules are isomorphic, then the two matrices are similar. So B is equal to P inverse for some matrix P. So what this is saying is every n by n matrix is similar to a matrix in rational canonical form. Now, when we constructed the rational canonical form of the matrix, we used a specific basis. We chose the basis, the components of the vector, to be powers of x, like this. But that isn't the only basis that we could choose for the module. And if we choose a different basis, then we can get a different form for the matrix. Next, we're going to choose a new basis that gives us a different form called the Jordan canonical form. Now, in order for the Jordan canonical form to work, we need to pick a specific type of field. We can't just have any field f. We need something called an algebraically closed field. And an algebraically closed field that has a lot of definitions. So the definition we'll use here is that a field f is algebraically closed if, in the polynomial ring fx, the only irreducible elements are linear. So as an example, C, the complex numbers, is algebraically closed. On the other hand, R is not algebraically closed because x squared plus 1 is irreducible in the real numbers. There's no way to write x squared plus 1 as a product of linear factors. On the other hand, in the complex numbers, we can write it as x minus I times x plus I. So we know in the complex numbers, if we're talking about irreducibles, we're talking about linear polynomials. So if we assume that f is algebraically closed, then all the irreducibles are of the form x minus lambda for some lambda in the field. One of the ways that we can write this direct sum of cyclic modules is using the elementary divisors. And the elementary divisors are always powers of some irreducible. So we can write this as fx mod x minus lambda to the power of d for some integer d. So let's suppose we have some polynomial cn x to the n plus cn minus 1 x to the n minus 1 plus dot 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 c1x and c0. Now, what we can do with this polynomial is repeatedly apply polynomial long division using powers of x minus lambda. So we can write this polynomial as cn times x minus lambda to the n, and then with some remainder. And this remainder is going to come from taking this polynomial and using polynomial long division, dividing by x minus lambda to the n. When we do that, the remainder is going to have degree n minus 1 or less. And so when we do this, once we have the polynomial over here that has degree n minus 1 or less, we can again do polynomial long division, and this time divide by x minus lambda to the n minus 1. So we'll have cn minus 1 prime x minus lambda to the n minus 1. And then the remainder is going to have degree n minus 2 or less. So we do it again, and then we keep doing this over and over and over again. Eventually we're just going to get down to the linear terms. We'll have c1 prime x minus lambda, and then the remainder will just be a constant. So what we've just shown is that we can write every polynomial in here as constants times powers of x minus lambda. And because we know we can do this, we're going to choose a new basis. For each polynomial x minus lambda to the d, we're going to pick the basis vectors x minus lambda to the d minus 1, x minus lambda to the d minus 2, and so on, down to x minus lambda and then 1. And this will also give us a basis for all possible polynomials. Now notice that this time I picked the basis vectors to go in the opposite order. So originally with the rational canonical form, we had 1, x, x squared, and so on. This time I'm starting with the highest power, d minus 1, and then going down to the constant term. The reason for this is that it turns out if you do it this way, then the matrix is upper triangular, which we like more than lower triangular. For the vector form, we just need to list the coefficients in order for each polynomial. This first polynomial here, we're going to have c1 and then d minus 1. And then the next is c1, d minus 2, and then so on all the way down. Those are just the coefficients on each of these basis vectors. And then we go to the next polynomial. It's going to have degree d prime instead. So we'll have c2 d prime minus 1, and then all the way down to constants. And then we'll have whatever remaining polynomials in the rest of the vector. Now all we need to do is figure out how we multiply by x for each of these basis vectors. And just like with the rational canonical form, we're first going to do it in the module, and then we'll translate that to what it looks like with the vectors. So let's suppose we have some arbitrary x minus lambda to the k. The first thing I'm going to do is note that x minus lambda times x minus lambda to the k, obviously this is going to be x minus lambda to the k plus 1. As a result, what we can do is add lambda times x minus lambda to the k on both sides. So we get x times x minus lambda to the k equals x minus lambda to the k plus 1 plus lambda times x minus lambda to the k. And so this gives us what we want. We've taken a basis vector, multiplied it by x, and expressed the result in terms of those same basis vectors. So in the normal case, this is going to be all we need. If we take a times some coefficient, say dot dot dot, and then somewhere in here we're going to have a 1. What happens is, remember that again the basis vectors increase this way. So first of all, when we multiply x minus lambda to the k, we're going to get x minus lambda to the k plus 1. So that's going to be the next component up. This 0 is going to turn into a 1. And then when we multiply x minus lambda to the k, notice we get lambda times x minus lambda to the k as well. So that's going to give us a lambda in the place where the 1 was originally. And then dot dot dot, everything else is just zeros. So this works, again, for every case except for d minus 1. But this time, the d minus 1 case is actually easier, because if we look at the d minus 1 case, what happens is we get this x minus lambda to the d. But this time, x minus lambda to the d is actually the thing in the quotient. So this is already equal to 0. We don't have to simplify at all. We can just take it out. It's always equal to 0 in this quotient module. And so if we look at what happens when we take this matrix and we multiply it onto a 1 up here, remember the highest one is going to be the first one, 1, 0, dot, dot, dot. Then what happens here is we just get lambda times that same thing. So we're just going to put, instead of a 1, we'll have lambda. Everything else is just going to be zeros. And so this gives us all we need. We can get to the Jordan canonical form of our matrix. So let's think about what this matrix looks like. Just like before, it's going to be a block matrix. So let's think about what happens. The first basis vector is the d minus 1 basis vector. And we saw that in that case, the 1 is just going to get turned into a lambda. So we're going to have a lambda right here. After that, in the d minus 2 case, we're going to have lambda times d minus 2, and then 1 times d minus 1. So there's going to be a 1 above for the higher exponent. And then again, lambda 1, and then so on, and then at the bottom, again, it'll still just be lambda 1. So this is our first block. And then the next block is going to be the exact same. It's going to have some different value. We'll call it mu. Mu 1, dot, dot, dot. And then it's going to look the same. All the other blocks will also look the same. And that gives us the Jordan canonical form of our matrix. And just like we saw with the rational canonical form, we can show that every matrix over an algebraically closed field, something like the complex numbers, is going to be similar to a matrix that's in Jordan canonical form just like that. So that's how we show that every matrix is similar to a rational and Jordan canonical form. We first write it in terms of these cyclic modules, and then we look for a basis and say what happens when we multiply by x. And that's what gives us these matrices. And because the original matrix has an fx module that's isomorphic to this fx module, we know that the two matrices will be similar.